Okay, so today we continue a little bit from our task last I think last Tuesday, right? So last Tuesday, so I see the works of all of you. So everyone done is okay lah. Everyone can run or simulate basic CFD, okay, on mixing tea, okay. So just follow the workshop that I provided, so you can simulate it nicely lah, right? So the objective is not to simulate it correctly, but to make sure that you comfortable with all GUI, all the buttons, where to generate mesh, where to view the contour, velocity, and so on, etc. Okay. If I see here, for example, cik Wan Fairuz ni, okay, everything is okay. Ada extra kat sini. We have a flood reports, and then we have total heat transfer. Okay, total heat transfer. Right. So they shown the geometry, meshing, okay, velocity contour and maximum temperature, right? So Encik Wan ni dah buat sekitar 73,000, banyak jugalah, 73,000. Okay, kenapa dia ukur mass flow rate ni? Supaya we need to ensure that we have several inlet here. Okay, if you remember, we have inlet Y here, inlet Z, and then outlet Y. Okay, so the total of inlet and outlet must be zero. Okay, must be zero. That's why we should have plus 106 plus 75 and minus 182, right? So minus is referred to outlet, okay, and then total is nearly zero. Okay, maybe it's not perfect, okay, but it's nearly zero. The perfect one, it should be 0.0000 something lah, right? So this one is considered okay lah. Okay. Right. If you can see the Cik Fakrullah pun sama. Okay. Ini banyak betul elemennya. Sampai 65,000 elements. So banyak lah. Right. So kalau guna student punya version, we are limit to 512K 512K element. Okay. So kalau tengok the result is same. Okay, you have continuity. So net result is 0. Alright. So this graph is referred to residuals. Okay, residual. You have continuity, S velocity, Y velocity, Z velocity, energy K and epsilon. K and epsilon is referred to the turbulence. Okay, if we switch on turbulence button, so they will come up with this option. Okay, for the basic, if you only have flow without temperature, continuity, and XYZ. XYZ for 3-dimensional. If 2-dimensional, you only have for X and Y. Okay, so the iteration here, it goes down, it will goes down. Okay, the more it goes down is better. Okay, it's more accurate. For example, for continuity is only up to 1 to the minus 2. Okay, 1 to the minus 2. Less accurate lah. Okay, it should be less than 1 to the power of minus 3 actually, right? On the default setting. Okay. If I can show this figure, okay, this figure is referred to kalau saya boleh buka. Slow lah saya punya laptop ni. Okay. Kalau saya boleh buka our fluent. Okay, our fluent. This is our fluent. Still loading, still loading. Oh, lambat betul ni. Okay, masih lagi. Tak boleh jadi ni. Alright, ini contoh yang lain lah. It's not the missing T, right? It's different. Okay, so so the one here, one is here. The graph here you show that you provided here, right? Is referred to the solution monitor, okay, under residual. Okay, this one, right? So this one. So we have a continuity x velocity, y velocity, and z velocity. So this one is different case. Okay, this one is different case. But if you open missing T, you should have energy K and epsilon, 3 more, right? And then this is the criteria. This one is 1 to the minus 3, 1 times to the 10 to the minus 3, same 0.001, 0.00001. So this one is the criteria, right? So the convergence will stop when it reach at least 1 to the minus 3 for all equations, right? But this one is not stopped. Okay, it's still running actually, right? Because we limit the iteration until 140. If we done the iteration like say 1,000, right? 2,000 iterations, it will automatically stop when it reach 1 to the power e exponential minus 3, whatever we set here. Okay, whatever we set here. The best practice is 1 to the minus 6, okay? 1 to the exponential minus 6, right? This is the best practice lah. Okay. Okay, this is iteration. How this is defined, I will explain in next part. Right? Let me close this, right? And then we open the. I will open the slide for lecture. Right? Okay, I have provided this note in Ulen. You can refer to Ulen as well. No. Tanya. Okay, finite volume method in CFD. So we will refer what this method is used in Fluent. Okay, we have several methods such as finite different methods, finite element methods, and finite volume methods. The one used in CFD, particularly in ANSYS Fluent, they use a finite volume method, right? So fundamental law of fluid flow, the equation used for the FVM, or we call it FVM. FVM referred to finite volume method. We have conservation of mass. Okay, conservation of mass, and then number two, we have conservation of momentum, right? This is referred to F is equals to ma. Okay, F is equals to ma, also referred to Newton second law, right? Newton second law, right? And then this is referred to conservation of mass, which is in, okay, mass equals to mass dot out. Okay, whatever in mass equals to whatever that out. Similar to the one we simulated, that missing T, okay, the total of flow rate in is equals to out. Okay, and we add all together, it will become 0. Okay, so let's say we have one particular example. We have a flow in a channel. Okay, let's say we have flow in a channel. Let's say in a pipe, we have U in the left. Okay, U in, and then at the outside is P out. P out is biasanya kita refer kepada atmosphere lah. This one is referred to P ATM. Okay, P atmosphere. Right. So this one is U inlet, velocity inlet. Right. So we need to find, let's say we need to find velocity and pressure distribution along the channel, and also the wall friction. Okay, wall friction. So we need to simplify. If you remember flow channel, if you have pipe, okay, we can simplify. Let's say we simplify as a steady two-dimensional laminar and incompressible. Incompressible means the rho is not changing. Okay, density is not changing. It fixed density, right? Then steady means it's not depends on time. Okay, it's not depends on time. We simulate until if it depends on time, we simulate until t is equals to infinity, right? And 2D is just a two-dimensional. Laminar is laminar. For the pipe, Reynolds number must be less than 3,000. This one is for laminar. Right? So Reynolds number is defined as, if you remember from degree or from bachelor study, rho UD over viscosity. Okay, rho UD over viscosity. If it's over 2,300, then we need to choose a turbulence model in our simulations. Okay, so we have so many turbulence model in Fluent. If you remember, we have K epsilon and so on and etc. Alright, so the governing equation, what is conservation of mass and conservation of momentum? If you remember from our last slide, we have conservation of mass, momentum, and energy, right? But our problem is just a flow in laminar, okay? Flow in channel, okay? Flow in channel. This doesn't involve temperature, so you no need to include conservation of energy equations. Okay, this one is for temperature or energy temperature, right? So this problem is no temperature, so no need to include energy equations. Okay, so we only have conservation of mass and conservation of momentum. Okay, so these equations is basically simplification or short form notation of full length of equation. Kalau boleh buka semula, if you can open slide number 1 or lecture 1, I have provided the governing equation in full form. Let me see. Okay, governing equation in full form, you have du over dt or du over dx plus dv over dy is equals to 0. Okay, so this is full notation lah. Full notation. Right, so this one is just simply or short form notation. Okay, this one we call as material derivative. Okay, material derivative. Alright, sama dengan conservation of momentum. Okay, sama saja conservation of momentum. You have a full notation as well, and then you have the short form notations. Right. So going back to our problem or flow in channel here. So we have V for each equations. Okay, for each equation here we have 3 equations. Okay, 1 equation in conservation of mass and 2 equation in conservation of momentum. This one is we can separate into x and y. Okay, x and y direction. So we have three equations. 1 in conservation of mass and 2 is in conservation of momentum. How many unknowns we have for this problem? Okay, for how many unknowns? We have velocity, right? We have velocity x, we have velocity y, and also we need to find pressure. Okay, so this is unknowns in our problems. Ux, velocity in x directions, uy, velocity in y directions, and p, pressure. Pressure is known as y lah, it's a scalar quantity, so you have only one value. Alright, so the unknowns is u refers to x direction, v refers to y direction, and pressure. Okay, so you have three unknowns to solve these equations. Okay. Right. So basically, so you have 1 equation for mass, 2 equation for momentum. So 3 equation through 3 unknowns we can solve. Okay, we can solve 3 equation and 3 unknowns. Okay, and then boundary conditions. Okay, boundary condition can help us to solve our problems. Okay, to solve our problem, like what we do in mixing T. Okay, in mixing T kan. Macam mana? Okay, you have inlet here. Okay, V1, and then we have V2, then we have V3. Okay, this is we call a boundary conditions. Right, and also temperature for our mixing T case. T2 and T3. Alright. So kalau salah boleh tanya, ask. So so this is flow around channel. Alright, flow around channel. So at the left, we need to define boundary condition at every edge of our problem. It's called a boundary. Boundary is mean boundary, sempadan, right? Boundary. So you need to define whatever value you have at the boundary. So at here, at the left side, the velocity is, let's say, u bar. If we have velocity like this coming in, right? So the velocity in y direction, which is v, is equals to 0. Okay, it's no velocity in y directions, right? And then for top and bottom wall, okay, this one we call top wall, and here we call as a bottom wall. Okay, so we imply no slip condition. Okay, no slip condition means the velocity at over there is equals to 0. Okay, so if we can expect that how the flow looks like is if we have a velocity, let's say this is our velocity u, okay, we can expect that at the end of the channel, the flow is become like this, right? It's become like this. Okay, so here is u, okay, and at the wall, the u is zero. Okay, u here is zero. Sebab apa? Dekat dinding ni is no velocity lah. Okay, it's no velocity. Velocity dekat wall adalah kosong. Right, so we can state that u is equals to v is equals to 0. U is what? Velocity in x. V is velocity in y direction. Y direction. Alright. Okay. So P at the right side we have we don't know what is the value of U at the right side, but we know if we open this to the atmosphere, okay, so the P outlet is equals to 1 atmosphere, okay. Or in fluent, we can set that as a P gauge is equals to 0, which is P gauge is equals to 0. Okay, sama lah. It's same with P atmosphere is equals to P ATM. Alright, so now we come into finite value method. How we want to solve this using computer or using FVM or the fluent, what they do at the background, at the black box. So how do we solve this model numerically using FVM, finite volume method, right? So the first step is to divide domain. To divide domain. To divide domain into multiple control volume or cells. Okay, to divide, the first step is to divide the domain into multiple control volume or cell. Okay, so for example, here we have divided the domain into 12 cell. Okay, 12 cell. Next, we need to determine the velocity and pressure value at cell center. Okay, so there are 3 unknowns at each cell center, which is pressure and 2 component velocity. So in total, how many unknowns for this problem? Okay, so one note, okay, let's say this is our channel just now. So FVM works that we need to divide this into 12, or we can divide into how many nodes, what you want, okay. But in this example, I only divided into 12 cells. Okay, macam yang tadi yang kita buat dekat mixing T tu, right? On the mixing T, ada yang buat sampai 200,000 cell kan, 200,000 cell, so you have 200,000 lah cell. Cell is referred to element, same thing. Okay, is referred to elements, element number in a mesh. So let's say I divided into 12 cell, right? Like in the figure. Okay, so each cell they have 3 unknowns, pressure and 2 components. Okay, 2 common velocity. So here you have P, V, and U. Here also you need to find P, V, and U. At cell center, okay, we evaluate at cell center, P, V, U. So total we have 36 unknowns, okay, 36 unknowns, right, which is 12 darab dengan 3. Right, you have 36 unknowns. So you need 36 equation to solve this problem. Kalau 3 equation pun kita dah guna calculator kan. Kalau 36 equation ni, bayangkanlah macam mana. Kalau yang tadi tu macam siapa Cik Fakrullah kot buat sampai 200,000 cell. Okay, so you have 200,000 cell. or element, okay, darablah dengan 3, okay, pressure, velocity and velocity. You cannot darab dengan 3, you need times 5. You have velocity in x, y and z, and then you have pressure and we have temperature, so you have 5 for the mixing tea problem. Like last Tuesday we make, so you need times 5, so become 100, 1000 lah, okay, 1 million. 1 million equation lah, okay, 1 million equation to solve. Okay, alright. So we need to find the value unknowns at each cell center, okay. At dekat center ni kita kena cari unknowns dia, PVU, PVU, PVU. Alright, so macam mana, how we want to find? Okay, let's say we have a 36 unknown value. So we would have to generate tak keluar. Kenapa dia tak? Okay. So let's say we have a 36 unknown value. Okay, so here we have 36 unknown value. So we would have to generate 36 algebraic equations. And these equations are generated by performing a control volume balance for each cell. Okay, so each algebraic equation will relate a cell center value to its neighbor. Right. So how we want to find? So we need to generate a control volume. Okay, control volume means, so you need to make a control volume here for each cell. Okay, control volume, and then there's another control volume, right? And then there's another control volume for each cell. You need to generate control volume, and we evaluate the balance for each cell. Okay, we evaluate volume. So in the finite volume method, this is done using the integral form of governing equations. Kenapa lagging? Okay, in the finite volume method, this is done using the integral form of the governing equations rather than differential form. Okay, so we have two forms actually. We have a differential form and also integral form. So for finite volume method, the one suitable is integral form, like this one, right? So this is the conservation form. Kalau full yang tadi, full notation, we have du over dx plus dv over dy is equals to 0. Okay. So this is differential form. So integral form is like this. Okay, this is integral form. Okay. Masuk integral form ni, if we can see that we have some integrate symbol ni, okay, and then we have s here, s here, and then we have 0 at the end. Alright, and we have 0 at the end. That's mean the net volume flow at any s is become 0. Let's say this is our s. Okay, this is s and s. So this is s lah. This is our s. Okay, s. So net volume flow yang masuk, yang keluar must be equals to 0. Okay, must be equals to 0 ini. Right? Sama juga example sama dengan momentum equations. Okay, momentum equations. Alright. So net dia untuk surface must equals to some force. Okay, kalau ini adalah untuk mass, continuity ataupun continuity lah, same. Here is mass, continuity. If we have another for momentum, same thing, MES. Okay, the net flow of momentum must equals to external force lah. Like this one is equals to 0, right? Must be equals to 0. Here must equals to some forces. Okay, viscous force and body force. Yeah, viscous force, right? So that is how integral form works. Okay, how integral form works. But it is not applicable to differential form. Tapi dia masuk yang sama. Okay, tapi cara nak olah dia adalah berbeza. So how to derive system of algebraic equation? How to derive system of algebraic equation? So we need to apply mass and momentum equation to each cell. Okay, average and interpolate cell center value to get the value at the control surface. At boundary, we use the boundary condition. Okay, so in this example, we will get 3 algebraic equation per cell, which is 2 in momentum and 1 in mass. 2 momentum is in velocity x, velocity y, and 1 in mass is for pressure. And I will have a total of 36 equations, okay, because I have 12 cells, so 36 equation, and should have 36 unknowns. All right. So this is how it works. Okay. Let's say I have this. Saya lukis balik, tak apa. Saya lukis kat sini je. Alright. So let's say I have 12 cell. Okay. And I select cell number 1. Okay. I select cell number 1. Yang warna kuning ni, I select cell number 1. Okay. So I want to evaluate the flow at the interface. Okay, I need to evaluate flow at the interface here. Color biru. Okay, so I need to evaluate flow at the interface here. Alright. So the flow rate I define as Q. Okay, let's say saya tulis balik lah. Let's say Q for mass flow rate between which cell? Okay, between cell 1 and cell 2. Okay, between cell 1 and cell 2. Let's say I have flow here. Okay, so I name it as Q1, 2. Okay, so the flow between 1 and 2. Okay, flow rate apa rumus dia? Okay, flow rate, what is the rumus? Flow rate, the formula is velocity times area kan? Area. Okay, velocity times area. Let's say that is the flow rate lah. So you have velocity, let's say U, okay? U. Let's say I have velocity here, okay? U between 1 and 2, okay? Between cell 1 and 2, dekat surface, dekat cell surface, dekat boundary ni, okay? 1, U1, 2, alright. Darab dengan area. Area dia adalah delta Y lah, okay? Panjang ni let's say delta Y times distance perpendicular to the screen, okay? Perpendicular to screen. Let's say this is 2-dimensional, I just make it 1 unit, so we just times with 1. If you have some distance at the perpendicular to screen, then We need to find what is that value lah. But this is two-dimensional, then I just take at 1 lah. Kalau saya lukis dalam 3D, mungkin lagi nampak lah. Okay, let's say saya lukis dalam 3D, right? So this is the face yang saya nak evaluate, Q12, alright? So this is number 1, okay? Yang sebelah sini adalah cell number 2, right? So the flow in between 1 and 2 adalah the flow between 1 and 2 is velocity between 1 and 2 times y. So here is delta y, okay, and here is 1, right? So surface area, surface area times 1, okay. So of course there will have some error, okay. Use this plus error, okay, plus error, because the value of velocity at 1 and 2 we do not know lah, right? Okay. Ke situ boleh right. Okay. Okay. Right. So what is 1-2 actually? Okay, what is 1-2? Yang ini. Ni apa dia ni? What is this? So that one is 1-2 is sebenarnya adalah u pada 1 plus u pada 2. We just divided by 2. Of course, it will generate some error. Okay, we don't know what is the value at the center. Okay, we don't know what is the value at the center. Contohnya saya ada satu temperature lah. Contohnya temperature lagi mudah. Right. So temperature kat sini, let's say temperature here is 30 degrees Celsius, right? And then temperature here is 50 degrees Celsius, right? So what is the temperature at the center ni? What is temperature at the center ni? Kita tak tahu, okay? We don't know what is the value, but we need to assume. So the assumption is 30 plus 50 divided by 2, which is 40 degrees C lah. So here is 40 degrees C. Okay, we just made the assumption. Okay, that one because that's why it's will generate some error lah that we don't know, right? So that is data U12, which is U1 plus U2, right? Okay, and then we plug in into the first equation. Okay, we can plug in the first equation. Yang ini kita masukkan saja dekat sini. Okay. Masukkan saja. So you will get Q12 is equals to masukkan saja. Jadi you dapat U1 plus U2 divided by 2 delta y plus 2 error. Okay, 2 error. Alright. Okay. Yeah, okay, so that is for one phase. Okay, one phase, right? One phase. So what happened for the second phase? Okay, for the second phase, so you need to add everything. Okay, we need to add everything between Q. We need to add everything for Q12 plus, let's say, Q12
Q13, okay, and then plus okay, Q13, and then plus here. Value here at the left, we know the value because it's a boundary, right? It's a boundary. So whatever value here, let's say 1 meter per second or 2 meter per second, we can include in our equations. Okay, and then in the top one, okay, in the top one, the value is 0. Okay, in the top one, the value is 0 because it's a wall. Okay, so we only have this face. 1, 2 face, and then 1, 3, 1, 3 face. Alright. Okay. Kalau saya boleh buat, if I can do one more, okay, for the 1, 3, okay, for the 1, 3. Okay, for the 1, 3. Let's say Q13, okay, at this face, okay, at this face. Alright. So you have, you cannot tell it as a U because it's in the V direction, Y direction, you should have V lah, okay. So which is V13 and then delta X, alright, times 1, alright. So you have V13 delta X times 1 plus error, okay, plus error, right? So what is V13? So V13 is defined as V1, of course, plus V3 divided by 2 plus error, right? Plus error. Okay, and then we can plug in back. You have Q13 is equals to V1 plus V3 divided by 2 delta X plus 2 error. Alright. Okay. Okay. So boleh apa lagi? So yang ini kita boleh simplify. Okay. Cuba simplifykan dia. Oh, mak. Padam. Saya padam macam tu je lah. Okay. Okay, yang ini sebenarnya menjadi U1 over 2 plus U2 over 2, right? Delta Y, plus 2 error. Yang ini dapat V1 over 2 plus V3 over 2 delta X plus 2 error. Okay, addkan semua. Okay, addkan Q12 plus Q13 plus whatever value dekat sini, plus whatever value kat sini kalau ada. Okay, sini kosong lah sebab sini wall. Sini you have some value. So you will add up with these equations. Right, this equation which is U1 plus U2 plus V1 plus V3 and E. A, B, C, D and E is referred to inilah yang ini, addkan dia, add. Okay, akan dapat yang equation ini lah. Alright. So A, B, C, D, E itu is referred to the coefficients. Okay, is referred to the coefficients. Right. So you will have 36 sets of these equations. Okay. So this is one equation. So you need to have 36 sets of equation. So if we solve in matrix form lah. Okay, basically it's solved in matrix form. If we solve it in the MATLAB, okay, if we solve in matrix form. So if in ANSYS, if we do it iteratively, okay, to solve 36 set of equations. Okay. All right. Okay, so algebraic equation can be derived using physical argument or integral form. So the one I do here is a physical argument lah. If you want to try integral form, this one we call integral form, we can do, okay, can do, but it's quite complicated lah. But for the complex geometry, integral form is much more reliable lah compared to physical argument. So this one is just a peta je kan, rectangle shape. So physical argument is much more suitable lah and much more easy to understand, right? So we calculate a flux phase by phase. Okay, this means mass leaving CV is equals to mass entering. Okay, so if you have a Q12 here, let's say this is our Q12, it's minus for the cell 1, but it's positive for the cell 2. Right. Sebab dia berkongsi phase yang sama, it share the same phase. Yang warna pangkah hijau ni, the cross green ni. So the Q12 is positive if you refer to cell 1 and then positive if you refer to cell 2. Okay, and the value is same, right? If we have here is 5 meter cube per second, okay, same. The one left leaving cell 1 is same value the one entering the cell 1. Okay, so we can call that the conservation is guaranteed for each CV. Okay, so conservation is guaranteed for each CV. So it's no issue that it's not conserved. Okay, kalau tak conserve pun disebabkan oleh error itulah tadi yang kita buat belakang. Alright, so in the end, kalau saya susun balik equation ini ke belakang, okay, you will get E is equals to 0 lah, is equals to 0. Okay, alright, is equals to 0. Okay, so we will do with this iteratively. We will do this iteratively until at some point. Okay, so when we want to stop iterating, macam kita buat at the mixing T kan, we iterate until 200 iteration, 140 iteration. So when we need to stop iterating? Yeah, okay. So solution to algebraic equation after each iteration must satisfy. We replace 0 just now with R1. We call it as aggregate imbalance. Okay, we replace this 0 with the R1. Okay, R1. The aggregate imbalance also we call as a mass residuals. Okay, mass residual. It's also referred to the continuity residuals. Okay, we will stop iterating when this aggregate mass imbalance is less than some tolerance. Okay, and then tolerance is default is 10 to the power of minus 3 influence solver. Okay, the same ideas apply to the momentum equations. Okay, in any part of momentum outflow that is not balanced by force is an error, is a momentum residual. Okay, so the one yang kita evaluate dekat fluent, okay, must be less than, must be approaching 0. Okay, must be approaching 0. So the ones here, R1 ni sepatutnya kosong lah. Okay, mustahil dapat kosong, tapi kita akan dapat satu nilai. Let's say we get one value, but the value must be less than some tolerance. Okay, so this value, aggregate imbalance, is referred to the one that we simulated last week. Okay, the one we simulated last week. Let's share again. Okay, the one we simulated last week, which is yang ini. Yang ini. Yang graph ni. Right? So let's say the continuity. Right? The continuity, the black color. Okay, and so each iteration it will iterate until the aggregate imbalance is fall within some value. Okay, fall within some value. It will not approaching zero. Okay, if you can approaching much more zero, is okay lah. It's much more accurate. Okay, for this one is only around, I think, 1 to the power of minus 2. Okay, in fact, in Fluent, they have set the tolerance is berapa tadi? 1 to the minus 3 lah. 1 to the 10 power of minus 3. Okay, so this is for continuity. So this is mass imbalance that we talk about. Okay, so they evaluate for each iteration. Okay, so the example I show you just now is for continuity. The same concept. Okay, the same concept apply for the x velocity, y velocity, and z velocity. Right? Okay. Alright. Okay, Sudah pening. Macam sudah tunjuk. Then I want to show how to plot graph. Okay, saya nak tunjuk how to plot a graph. Or I will show this first. Okay, tak apalah, kita teruskan dengan lecture seterusnya ni. This slide also I have uploaded in Yulian, so you can refer. So one is the grid. One is the criteria for the verifications is grid independence test. Okay, grid independent test is like compulsory for any simulation works, particularly in CFD or in FEA, right? You must done the grid independence. Okay, like what we have done last Tuesday. Okay, okay. For example, Farisha done around 29,680 element. Okay, what if Farisha naikkan mesh ni, let's say 50,000, okay, let's say 50,000, is it you will get the same maximum velocity? If you use 29,000, you get maximum velocity of 21. If you do 50,000, let's say, is it you get still 21 or you get another value? So that is we call a grid independence. Okay, if you get another value, that means your grid is not refined enough. Okay, your grid is not good enough that your answer is changing with the value. So we must test our grid so that we increase several grids until we satisfied that our answer is not much changing. Okay, by practice, it's less than 5%. It's okay. Okay, less than 5% is okay. Much more lower is better lah. Alright. Okay, grid independent test is, or we call also mesh sensitivity study, is the part of verification in CFD. Okay. Right. It's done to ensure the result is not depends on the mesh size. Okay. To ensure the result is not depends on the mesh size.
The result is expected not changing after certain number of mesh that we use. Okay. The successive grid element number must be larger than 1.3. Okay, what it means? Must be larger than 1.3. Let's say our case. For example, Immanuel. Okay. Immanuel pun banyak juga. They've done around 232,000 elements. Right? They get the maximum velocity of 12. Okay. If you want to test the next grid, okay, it must at least 1.3. Okay. So next grid must be 231919 mestilah times 1.3. Okay. Mestilah at least 30,1494. Okay, if you want to test, right? And then the next grid, you must times 1.3 more, at least. Okay, if you get largest, better lah. If you have 2 times, okay, at least minimum is 1.3. So next grid must be, let's say you times 2 this time. 2. It's okay. Okay. Next grid must be 60,000. Okay. Sebab apa? There is student that doing the reports, they do grid independent test, but the next grid is so close. For example, for the first grid they run for 23,000, and next grid is just run for 24,000. Of course, the max velocity is, of course, the value of interest, such as velocity, is not changing because the element number is so close. Okay, so we cannot verify that. We call the grid independent test because the element number, the increment is so low, right? So the rule is at least 1.3 lah. The higher is better. Alright. Okay. Alright. So this is our case. Okay. If you remember, for our last Tuesday, right? We have the fluid flowing inside the pipe. The fluid temperature at inlet 1 is 12. Okay, this is one example lah. Inlet velocity V1 is 10 at inlet 2. At inlet 2, the fluid temperature is T2 60 degree. With the inlet velocity V2 is 6 meter per second. Okay, so conduct grid independent study. Right. So this is case study. So if we done, let's say, 5 different grids for this test, okay, grid A, B, C, D, and E, okay, for examples, and then we rename it as grid 1 until grid 5, right? Okay, grid 1 until grid 5. So grid 1 have much more lower grids. Until grid 5, they have around 683,000 element. Okay, kalau kita run pakai yang student version, tak boleh lah ni. Sebab dia dah exceed 512. Okay, 512. Okay, never mind, it's okay. So the successive grid for this case, for this particular case study, divide 53 divided by 27 plus, so you get 1.9. Okay, for this grid you have 2.8. For this grid you have 2.1. For this grid you have 2. Okay, so all are over than more than 1.3 ratio. Okay, and then we evaluate the maximum value of skewness. Okay, make sure it less than how much? 0.95. Okay, 0.95. And then minimum orthogonality must be larger than 0.001. Okay, so everything is passed lah. Okay, everything is okay. Right? Okay, so the result.
Okay, so the result here is we can see that between grid number 1, grid number 2, same, almost same. But when it's jumped to grid number 3, okay, you see that the green color is become like this lah, compared to here is much more diffuse, okay, and then this one is become much more symmetry, okay. And then when you try for grid number 4, which is much more higher, okay, the green color temperature ni, okay, dia become jadi timbul dia macam ke bawah sikit. Okay, dia ada satu recirculation lah kat sini, okay, recirculation. And then same with this number, grid number 5. Okay. And then based on this, okay, yang mana kita nak ambil? Okay. So kalau saya ambil yang nombor 4 lah. 4. Okay, sebab apa? Dia akan tepat lah. Alright. Can I take number 5? Can. Okay, boleh. Sebab result dia sama. Kalau ikut visualize dia sama. Same. Right. But if I run for pseudo version, I cannot get this grid. Okay. Or if I run using lower spec laptop, I cannot generate much more than 4. So I can select for 4. Okay. So it's computational cost saving lah. Okay. It depends on your time, how much time you need to solve the problem. Okay. If you have the enough spec for PC, okay, it's all counted lah. Alright. So you can choose number 5 or number 4, but for optimally, you can choose number 4. If you want to choose number 3, you will not get the accurate result at the end of the wall. Right? So grid number 4, around 336,000. Right? That is based on contour, based on contour of temperature. Okay. Tapi kalau kita tengok dekat velocity, tak ada beza pun, tak ada beza. Okay. It depends on what you want to obtain. Okay. If it goes back to your goals. If your temperature is more important, you select grid number 4. If your velocity is more important, maybe you can select number 3 or number 2 because it's not much different in value. Right? Okay, that is how we look at the contour. Alright, so if you refer to the grid or quantitatively based on value, we make a table like this. Okay, we make a table like this, and then we state down whatever value that we need. For example, maximum velocity, 18 meter per second for grid number 1. 19.071 for grid number 2, right, and so on and so forth. Okay, temperature pun sama, kita list down kan ya. Okay, kau tengok sini, kau tengok kalau kita lebih interest on the maximum temperature, we can select grid number 3. Okay, because the difference is not much different if you're using grid number 4 or number 5. Okay, if we choose grid number 2, the difference is around 4 Kelvin. Difference is around 4 Kelvin. Okay, so if you choose number 3, the difference with number 4 is less than 1 Kelvin. So better you take number 3. Okay. So one way to do this is you can also calculate the error. Okay, let's say you want to find what is error for grid number 2. Just do a simple error calculation. For example, grid to error, you just calculate that based on what? For example, based on temperature. Okay, let's say based on temperature, you have 327.451 minus 326.734. Okay, divided by the final mesh. Okay, for this one, the final mesh is 327.451, and then you times dengan 100 lah. Okay. Alright, times dengan 100%. Okay, so repeat for each grid. Okay, repeat for each grid. For example, you want to do grid number 2 error. Okay, then you can choose the one that is lowest error percentage. Right. For example, this one is 331.174, right, minus 327.451 divided by 331.174. Alright, so on and so forth. Okay, so choose the lowest error. Okay, the best practice is if you get less than 5%, consider okay, right? It depends on your requirement. It's no right or wrong, right? There's no right or wrong. Okay, so we have several methods. This is method number 1. If we view based on color or contour, and number 2, we view based on this particular point, particular value. Okay, and then the other way is we view based on graph. Okay, let's say we choose one line. Okay, a temperature against distance at center line of the vertical pipe. Okay, let's say we want to plot. We make a one line. We want to plot a graph along this vertical line. Okay, so you can plot this line. Right, so you plot for each grid number 1 until grid number 5. Okay, so we can see that sama, result sama. Mana satu grid number 1 yang biru pekat di bawah sekali. Okay, grid number 4 atas. Okay, grid 3 yang paling tak tepat. Right, so you can choose the one is close each other. Okay, maybe in this case I will choose grid number 4. Maybe grid number 4. Grid number 1, grid number 2 pun macam okay kan. 1, 2 pun dah dekat lah. Choose the one is closest. Alright, choose the one is closest. Macam ni semua okay ni. Ini contoh yang tak okay lah ni. Patutnya grid 1 jauh, 2 dekat sikit, 3 lagi dekat, 4 dekat, 5 lagi dekat. Pilih atas satu sama lain. Okay, so macam mana dia plot graph ni? So kau boleh tengok dekat our project. Okay. Okay, so launch proven. So jom nak tunjuk macam mana kita nak plot graph. Maybe useful for your assignment. Tengah loading. Sekejap. Okay. Ini ada solution ke belum? Kejap tengok. Okay, kalau kita run, tengok kat sini, we check at graphics. Counter unavailable. Maknanya dia belum run lah. It's not yet run. So you don't have data. Okay, you don't have data. Right? Okay. Maybe we try save lah. Save iteration. Okay. To run again, you can initialize. For each time you want to run, you must initialize. Okay. Okay. And then run calculation. Right. Okay, I just run for maybe 10 iteration, just for examples, right? Then calculate it. Okay, so it's done. So my result is not nice. Okay, you can see the iteration is only up to not even 1 to the of minus 1, the mass imbalance of residuals, right? Okay, for example, I want to plot a graph on the center line. Okay, you need to view the contour first, or view geometry. Maybe I select velocity, or you can select any parameter. Okay, so here I have velocity or temperature. Okay, so right. So if I want to plot a graph for this particular geometry or problem, angkat balik. Okay, so you need to, under result here, under result you have, I minimize it. Okay, under result you have surface graphics plot scene animation reports. So under plots, okay, so you can try the others, but I want to show what is SY plot here. Okay, SY plot. Ini kita akan banyak guna lah, okay, for any report engineering, right? So you have a solution SY plot, SY plot name, right? And then you need to define where you want to plot. For example, I want to plot along this line, the center line, right? So you can select new surface to define the line first, to create the line first, right? New surface. And select line, or rate. Select this one, right? So you need to select, if you know what is the coordinates of 2 points, okay? To generate a line, you need 2 points. Okay, you need to point 1 and point 2, and then they will bersambung lah, line point tu akan jadi line. If you want to create a surface or plane, you need 3 line, kan? Kalau nak surface atau plane, kita ada 3 line lah. 1, 2, 3, you dapat surface, kan? Kalau 2 saja, you akan dapat line, right? So this is endpoint lah, between point 1 and point 2. If you don't know what is the coordinates, you can select with mouse. Okay, click here and select with mouse. Right click, okay, and then it will appear the red button lah. Okay, and then pusing ke bawah, select point yang kedua here. Okay, and then they will appear here lah, dekat sini. Okay, so this is coordinate of point 1. This is coordinate of point 2. Okay, if you agree, you can create. Okay, now it's appear in here, line number 4. Right, line number 4. Okay, to start plot, what you want to plot? For example, I want to plot pressure, right? Pressure. Select pressure and then click where you want to plot, and then which direction. Saya rotate balik. Okay, which direction? Okay, so this direction is referred to the y-axis, kan? Hijau ni. This is y-axis, right? So select y is equals to 1. Yang lain jadikan kosong, right? And then we click plot. Okay, you get the plot result lah, right? So from bottom to the top, right? If I want to export this in external files and plot this graph in Excel, for example, you just click write to file. Yeah, write to file, and then write. Okay, you can save at your local drive. For example, I save dekat mana? Saya save dekat desktop. Desktop okay, save kat desktop. Right, under CAE 12 April. Okay, XY plot pressure. Okay, and click OK. Right. So lihat balik file kita tu kat mana. From mana file ni, CAE 12. Right, CAE 12 April. So ini lah saya plot tadi. Okay, you can open first using any I think notepad. Okay, you get this type of value. Okay, copy saja. Copy. Right, copy this and put in your Excel file lah. For example, saya create satu kat sini saya create paste lah. Boleh. Okay, boleh. Right. So this one is what? This one is distance. Okay, this one is distance, and this column is pressure. Okay, pressure. You can check again. Okay, this one is pressure. So you can plot. You can do whatever you want once you have the data. Okay. All right. Okay. Let's go back to the post processing. What we have on the post processing. If we click at result, okay. So belum keluar. Okay, dah keluar. Okay, it's there. Alright. If you want to show, let's say temperature or velocity at particular locations. Okay. For example, I want to show temperature at outlet. Okay. You just select location, outlet, variable, temperature. Okay, and then you click apply. Okay, pusing sikit. Okay, so you can get the temperature counter lah. Okay, this is global or local is referred to global for the whole things. Okay, the whole geometry, but for local is for specific location we choose. Okay, if we choose a local, it will only show maximum or minimum at the outlet. If you choose local, it will show at the whole locations. For example, for global, you have 363. Okay, and then for local, we can apply. You get 308. Okay, that means this is only for the outlet region only. Right? Kalau kita pilih global tadi, jadi 363. 363 tu bukan kat sini. Dia dekat lain. Mungkin dekat inlet ke, dekat wall lain lah. Dekat lain. Right? If you want to specify based on our location, you select local. Right? So this is counter. If we change this to let's say 100, it will become much more. smooth lah, alright. This is the functions, right? Okay. If you want to include the vector, kat atas ada banyak. You have, let's say, here is, I think here is vector kan. Here is vector. Okay. Include vector location dekat mana? You can put any location. Let's say, saya pilih outlet juga. Outlet, apply. Okay, so you can see vector, but tak nampak lah sebab ada contour sekali. So you need to off your contour. Right, so you left with vector. Okay, nak besarkan dia, you can change the value. Pula 0.5. Dia kena type error juga ni. Error. Simbol size ni besarkan. Right. Okay. And then is there any animation we can show? This one is for time step. This one is for animation. Okay, if there any animation, you can click for animation. Dengan syarat, we must save our simulation first dekat sini. Under, I think under solutions, run calculation activities ni. Okay, so this one you need to save lah, auto save every iteration. Okay, just change this from 0 to whatever value, maybe 1 ke 2, okay, you can choose. Right, kalau 1 for every iteration you can save, tapi dia akan makan banyak space at your laptop or PC lah. Right, bayangkan if you have 1,000 iteration, so thousands file dia akan save. Okay, for much more iteration, let's say 1,000, maybe you can save for each 5 iteration, okay, 10 iteration you can save. Okay, so tak perlu save so many file in your hard drive. Right, so ini boleh save. Okay, kalau nak save pun boleh. For example, ini tak nampak lah. Saya tengok kat sini lah. We change this contour, we view at wall solid. Okay, mungkin lagi nampak. We view at wall solid. Right, and then temperature. Okay, so for this we try make a animation. You can click at here. Dia tidak habis lah. Okay, and then we can save movie. Let's say kita nak save at kita save kat same folder. Alright, tekan save, and then we try to run lah. Okay, we try to run. Okay. Okay, rasanya dah siap. Klik play ni dia akan terus automatic save lah. right? Bila habis dia akan save. So we can see again our file is save ataupun tidak. Mana dia save? User file. CAE class Tuesday user file under Tuesday files user files. Kat sini. Okay. Kembali folder ni. 5 user file. Okay. So dekat sini lah. Buka pakai apa-apa. Okay, choose any. Right. Terlalu dekat sangat. Okay. Cantik lah. Okay, sebab kita buat cuma 10 iteration, so tu yang dia cepat. If you do for 100 or 1000 iteration, you can see lah the animation, right? Okay. Right. Okay. Ada soalan tak? Okay, this is a picture animation, alright. So next things, lagi. I want to show you how to import geometry. Okay, how to import geometry. If you draw something in, let's say SolidWorks or AutoCAD or CATIA, you can import geometry into the design modeler and we can run a simple simulation. Okay, for example, we do some aerodynamic study. Okay, tarik balik. We create a new project. For example, we run the car simulation. Car simulation, right? Okay, under geometry, files I have uploaded in uLearn. You can see the geometry car. Okay, this is car geometry. Okay, you kalau nak buka ni, you kena right click and save link as. Okay, you can right click and save link as. So you can save lah. Okay, before we upload it. So for example, ni saya padam tu. Okay, the file that I give you is a stat file. Okay, standard file for any geometry. Kalau saya save, saya right click, saya save link as at our working directory. Stop. Okay, saya save kat sini. Name file is Araba stat file. Right? So if I open that geometry, okay, I click file, import external geometry. Import external geometry file. Ini. So go to our file Araba, right? This one. Okay. So click generate. Okay, click generate. Okay, so you can see this is our car. Okay, so you can check. So they have one body. Okay, you can rotate. You can rotate. How to rotate? Here, right? Here, right? Okay, this is small scale car lah. Alright, small scale car. Right. So we need to do these simulations. Okay, the flow around car, but for particular we need to define. Right, we need to define our domain. Okay, so in fluid flow, the one that we need to simulate is fluid, not the car itself. Okay, so we need to create a fluid domain for this car. All right, we need to create a fluid domain. Right. So how to create a fluid domain? You need to create like a box inside the car, and then we subtract the box and the car so that the car is become hollow, and then our fluid is become our box is become fluid. Right? Like we run the test in the wind tunnel. Okay, like in wind tunnel. Right. So first we need maybe we can change the units to Okay, you can choose any units if that's comfortable. And then we need to make a box. Okay, you need several method to make a box. You can do a sketching. Okay, you can make a rectangle, right? You can make for example, primitive here you have a sphere, box, cylinder, cone, and so on and etc. But the easiest way is we done through the using enclosure. Enclosure means dia automatic tutup lah kereta ni. Kalau kita buat box, tak mana-mana box dia buat nanti kan. So kita kena pindah, kena move box tu. Kalau if we choose the enclosure, automatic dia akan buat di sekeliling kereta ni. Right? So you can click enclosure. Right? Enclosure. So target body, all body. Okay, cuba kita generatekan apa jadi. Okay, dia terus jadi. Jadilah. Okay, dia terus dapatlah. Dia terus enclosekan dia. Alright. If you want to change the box size, okay, if you want to change the box size, so you can change using the value here. Let's say this is 30, you want to make it 300, and then change and click generate. So belakang ni panjang lah. So belakang panjang ni okay, sebab you need to see how is the flow dekat belakang punya flow lah. Right? So next we need to subtract. Okay, we need to subtract the box and the car. Now we have two bodies. We have car and we have solid. We have car and we have solid. But we need to only solid. This is referred to box lah. Kalau saya boleh rename dia box, mudah. Box. Okay. So kalau saya boleh rename, sudah rename, kemudian saya nak subtractkan box ni dengan car supaya car tu menjadi seolah-olah kosong. Okay, I want to simulate flow, not the car itself. Okay, it's like a flow around the body lah. Right, so what we can do is we can use a function. I think Boolean. Okay, Boolean. Maybe in SolidWorks it's called subtract. Okay, but here we have a Boolean. Okay, same things. The operation here you need to subtract. Okay, kita tolak box ni, tolak kereta. Okay. So tools body adalah kereta itu sendiri. Okay, target body is our box. You can try and error if not sure. Box we can apply. And tools body is car, right? Preserve tools body. If is it our we want to preserve our car or we want to subtract completely, so you need to choose no or yes. So here I choose no lah. And then we can generate. Okay, now we have two body or two parts. When I click generate, apa jadi? Okay, it left with box saja. Okay, car ni dah tak ada lah. Walaupun kita nampak car ni sebenarnya dia bukannya kereta semua ni, tapi dia kosong dalam tu. Okay, it's zero, apa ni, empty lah. Right? Kalau saya boleh view. Kalau saya slice kan sini, ini akan nampak kosong lah. Okay, so this is our body. Right? Okay, so we're done with the geometry. Boleh potong tak? Kalau saya potong sini, you akan nampak kosong, kan? Kosong. Right? Ini adalah function untuk view potong lah. Ini boleh off balik. Nak view balik, tengok. Right? So sebenarnya dia adalah kosong. Right? So we're done with geometry. Right? Geometry. Then we go into the meshing. So saya nak tunjuk yang kita nak, if you draw something in SolidWorks, CATIA, AutoCAD, you can save. You can save in step file. You can save in. I have tried the IGS. Okay, you can import IGS file, step file. Parasolid can import. Okay. So when you import file, you can simulate things. Alright. So if you're not comfortable with space claim or design modular, or you want to draw the complex geometry that requires SolidWorks CATIA, you can draw in SolidWorks CATIA, and then we import into the lenses. Okay, so next we are done with geometry. Kemudian pergi pada meshing. Ya.
Kalau untuk import geometri tu dari SolidWorks, nanti kalau saya nak import tu apa ni? Assembly punya, maknanya consist beberapa part. Boleh juga ah?
Boleh. So dia boleh jadi banyak part pun boleh, tidak masalah. Okay. If you have so many parts, nanti dekat sini dia akan ada banyak part lah. One part, maybe sini ada satu part je. You have 2 or 3, 4, 5 part lah. So kat sini ada banyak parts. Okay, sama saja. Okay, so this is our machine. Alright. Step sama, stepnya semua sama. Ada salah dia pakai apa geometri pun, stepnya adalah sama. So this is good idea. You can try to generate what the default mesh looks like. Sama pula. Okey, belum lagi. Sekejap dia tengah meshing. Apa lambat lah saya punya laptop ni. Sekejap tunggu dia. Meshing, lambat. Oh ya, nak pergi tandas ke? Nak minum air kan? Minum air kan puasa. Dah, okay, dah ke? Okay, sudah, alright. So this is our meshing, nampak macam teruk lah, teruk. So sizing dia, the sizing is quality. If we check mesh matrix, let's say orthogonality, orthogonality dia more than 0.95, tak okey dah ni, 0.95, okay. Skewness yang kena, okay, orthogonality must be over than 0.01, okay. Skewness must less than 95, 0.95. Okay, right. Skewness is also okay lah. Okay, so if you want to increase the element size, you can increase here by element size, right? If you want to change, let's say this is using tetrahedron. Under meshing ni, dia ada macam-macam, so tak cover ni, tak sempat nak cover. So you have insert method, okay. So we have, let's say, automatic method is referred to the tetrahedron lah. If we choose apply. So method ni banyak. You have tetrahedron, hex dominant, suite, descent, okay. Saya tak nak try banyak, nanti dia nak run balik lama. Okay. Dia banyak lah. Okay. So you can try, you can explore. Kat YouTube pun banyak cara nak explore, cara nak guna mesh tu. Saya delete balik. Alamak, dah kena run balik lah. Okay, alamak, kena run balik. Okay, tadi kita ada, we have, tak ada dah mesh. Alamak, run balik lah. Kenapa slow sangat ni? Saya format laptop ni. Okay, sementara tu saya akan teruskanlah dengan lecture, last lecture lah sebelum kita berhenti pukul 12. Alright. Okay. Solver setting. Okay, tengok pada solver setting. Alright. So in CFD simulation, you should not assume that just because you have an answer, the answer is correct. Okay. So by modify the solver setting, you can improve both the rate of convergence and then the accuracy of the computed result. Okay. So this is the common figure in any simulation works. Alright. So we set the solution parameters, we initialize the solutions, okay. We enable the solution monitor of interest. Let's say, like what you do in MMCD, if you want to view the flow rate or view the temperature, okay, you can view, okay, and then we calculate the solution, okay, and we check for convergence. If you not converge, we need to modify solution parameter or grids. Okay. What is mean by converge or not converge is that you can plot the results again iterations. Okay, and like you plot the temperature again iteration. Okay, it's not converge and then you need to modify. It's converge, you can check for accuracy. Okay, it's not okay. Go back to modify solution. Right. So influence, there are two kind of solver. If perasan lah, we have a pressure base, okay, and then we also have the density base, okay, density base. Dekat mana duduk ni? Pressure base and density base. Dia located dekat sini. Under general, under general you have pressure base dan density base. Okay. So what is the meaning? What is the difference? Okay, the pressure based solver takes momentum and pressure as a primary variable. Okay, pressure velocity coupling algorithm are derived by reformatting the continuity equation. Maknanya dia soft pressure dulu. Okay, soft pressure dulu. Two algorithms are available with a pressure based solver, which is segregated solver, and then a coupled solver. Segregated means they solve one by one. We will solve pressure first, and then we shall solve for momentum or velocity. Okay, when we talk about momentum, is referred to the velocity. Okay, when we talk about pressure, is referred to the continuity equations. Number two, we have a coupled solver or PBCS, which is solve pressure and momentum simultaneously. Okay, serentak. Okay, so like this diagram. So you have the pressure base and also pressure base coupled and pressure base segregated. Right, the soft momentum and then the soft for moment continuity secara berasingan. Okay, for the pressure they solve together. Right, and then we solve energy and solve species kalau ada. If you have temperature, we solve as well for energy. If you have combustion, like in combustion, you have carbon dioxide, you have oxygen. So that is referred to the species. Right? And number two, we have a density-based coupled solver. Okay, so density-based coupled solver is basically suitable for compressible flow. Okay, compressible flow, this is much number more than 0.6 lah. Okay, where density is changing. Okay. If you have this constant density, you can choose default setting, which is pressure base, right? Pressure based solver is applicable for wide range of flow, from low speed to high speed. Pressure ni boleh juga digunakan untuk high speed compressible lah, and it require less memory, allow flexibility in solution procedure. Okay, the pressure-based coupled solver or PBCS is you can use this for most single-phase flow. Okay, single-phase flow means you only simulated air, okay, or you only simulated water. Okay, it's not mixed up. Or if you have in one tank, like in maybe in an LNG tank, okay, you have oil at the bottom and you have some vapor at the top. So you want to simulate that. So that involves multi-phase. You have phase for vapor and you have phase for oil, right? So that is considered multi-phase, right? And it requires 2 times more memory than segregated solver, right? So number 3, we have density-based solver, applicable when there is strong coupling or interdependence between density, energy, momentum, or species. For example, we have a high-speed compressible flow with combustion. We have carbon dioxide, we have NOx, you have oxygen. Okay, you have a hypersonic flow or you have shock interaction. Okay, so this type of flow is suitable if you use density-based coupled solver. Right? Okay, ini saya dah cerita tadi. Influence solver variable are stored at the center of read cell. Okay, they can store dekat center. That how you want to find what is the value at center? We make the control volume. We evaluate whatever come in. Mass in plus mass out is equals to 0. Right? Okay, so the value of the interest are store at the center, okay, store at the center, but how we want to find the value at the face, okay. So this is what we have discussed. Macam tadi saya cakap, if you have a temperature 50 at the cell 1 and 30 at the cell 2, at the middle must be 50 plus 30 divided by 2. So you have 40 degree Celsius, okay. That one, if you use averaging, okay, averaging, or we call averaging. So that one is actually part of the interpolation function, okay. So this requires interpolating the cell center data, and these are set as a solution method. Okay, so interpolation scheme ni yang terdapat dalam Fluent dekat sini. Ini solution method. You have standard, momentum, pressure. Okay, pressure ni we use for standard first order upwind. So you have so many options lah. Alright. Interpolation scheme. You want to get what is value of the phase based on value of the center. Okay, we have first order, we have power law, we have a second order. Alright. So first order is referred to the, we take whatever value here. For example, here is 50. Okay, so for example, here is 50, then the other side is 30. We take whatever coming from the behind. Okay, or coming from the upwind. Okay, sorry, it's coming from the front. So here is referred to 30. Okay, it's not referred to 40. So there is a first order upwind. Easiest to converge or only first order accurate. Okay. So we have another option. We have power law, and then second order upwind. Use larger stencil for second order accuracy. Right. So we have also MMCD and also quiz. Right. Quiz is third order. Okay. MMCD is also third order. Alright. Tapi third order locally. Okay. For now, until 2020 now, is still under developing. Still we have second order accuracy at most. Okay. Yang ini tak, ini bukannya overall, just locally lah. Yang betul ni yang ini. Yang biasa kita guna adalah second order upwind adalah yang paling banyak lah. Ini catat. Sekejap. Okay, interpolation scheme for calculating cell phase pressure when using pressure-based solver in Fluent. You have this. Okay, you have standard, presto, linear, second order, body force. This option is not so critical. Okay, you can choose any option, or you can choose whatever Fluent have sediakan, prepare for you. You open dia dah tunjuk dah pilih-pilih ni. Just biar je. Okay. Or sometimes I think dekat bahagian run calculation ni, you can check case. Okay. If they asking you to change any model, they will recommend here lah. Okay, maybe say that use second order accurate for pressure. They will recommend you here. Alright, under check case. Before we click calculate ni, is the best practice to click check case. It will recommend you whatever suitable solver to use. Okay, pressure velocity coupling refer to the numerical algorithm which use a combination of continuity and momentum to derive equation for pressure by using pressure-based solver. Okay, we have 5 algorithm, which is simple, semi-implicit method. This is mostly we use for steady case. Okay, pressure implicit splitting with of operator. Mostly we use for unsteady case. Alright. Now this one also you can choose by default lah. No need to worry. Okay, this is just like a summary. Simple, simplex and piso. where's the located simple, simplet and piso? Dia ada dekat mana? Method. This one, under pressure velocity coupling. Okay, you have simple, simplet, piso, couple. So here you can choose any coupling yang okey lah. Yang tu pun you rasa macam kalau tak tahu pun yang pilih je lah mana-mana, tak kisah. Right, we know as a segregated method used for incompressible flow, Mach number less than 0.3. These three: simple, simplet, and piso. Less than Mach number 0.3. That means for incompressible. Piso is used for unsteady simulation with large time step. Piso also can be used for steady state simulations. Density state, density piso ini dia summary, okay, used for Mach number more than 0.6. New solver, new version of NC 17.2 above, they have this new couple solver. Okay, can be used in both regime with more efficiency. So Mach number 0.3 boleh, Mach number 0.6 pun boleh. Ini yang new scheme ni yang letak dalam fluent, which is couple solver. Couple solver. Right. Here is comparison data from solution of REE foil. Okay, if we use segregate pressure base or pressure base couple, okay, you see how many memory we use. So much more is done on the density base lah. Okay, time per iteration is banyak yang dekat sini lah, density base. Iteration to converge, if you use segregated pressure solver, okay, is around 2,570 to converge compared to the pressure based couple solver. Couple dengan segregate ni ada dekat mana lah? Sekejap kan. Tak ingat lah kat mana. Kau dah jumpa ke tak? Tapi itulah tetap letak apa ni. Pressure, security, kau operating ke? Monitor convergence, mana operating conditions? Cell zone. Bukan lah. Sekejap method lah kan. Jumpa lah, nanti cari balik lah. Ni cari balik. Okay, dia ada dua lah. We have segregate dan couple solver. Right. So basically you nak guna kalau macam contoh for this example, a solution on REE foil, you can choose any actually, right? But it's different lah. If you choose, it's not right or wrong. It's impact on your maybe time iteration lama, iteration to converge tu lama kan. Nak run tu lama, tu je dah bezanya. Tapi it's not right or wrong in your simulation. Right. Standard initialization, the solver works in iterative manner. Therefore, before the first iteration, a value must exist for every quantity, every cell. Okay, so this is your initialization lah. So that's why when you want to run new run, you must click initialize first. Okay, there are two types. One is standard, the other one is hybrid. Okay, the other one is hybrid. Okay, this one is what I have tell you. The case check is utility influence with search for common setup error and inconsistency. Alright, just click check case under run calculation. So it will tell that consider using higher order discretization for final solution. First order discretization may be used in initial calculation. Sudah dia punya recommendation. So gunalah third order ke MUCL or using second order, right? Based on the recommendation. Convergence, the solver should be given sufficient iteration such that the problem is converged. At convergence, the following should be satisfied. Okay. Macam mana kita nak tahu solution tu converge ke tak converge? The solution is not changed with subsequent iteration. Okay. The solution is no longer changed with subsequent iteration. So bila you iterate, solution tu dah maintain sama je. Okay, so itu kita boleh cakap sebagai converge lah. Overall momentum, energy and scalar balance are achieved. Like what you do in mixing T, you evaluate total flux in and out is equals to 0. Kalau dah sampai 0, we consider achieved. Okay juga. Number 3, all equation are obey all cells to specified tolerance. Yang ni yang residuals tadi, yang graf yang turun tu. Okay. Achieve 10 to the power of minus 3 or minus 6, we consider convergence. Okay, itu pun boleh. If we monitoring convergence using a residual history, generally a decrease in residuals by 3 order of magnitudes indicates at least qualitative convergence. At this point, the major flow features should be established. That means must be at least 1 darab 10 kuasa 3 lah, alright. And then the scale energy should decrease to 10 to the power of minus 6. Species 10 to the power of minus 5. Right, yang tadi. Yang iteration. Residual, okay. Under solution, monitor residual. This one, okay. This one is okay. Minus 3 is okay. Minus 3, okay. Minus 3, okay. Minus 3. Energy must be minus 6. Okay. 3, okay. If you have species like carbon dioxide, NOx, that one is minus 4. Minus 5. Minus 5. Okay, ini border. So, residual normally change level to 1 is minus 6. Okay, if converge criteria is set to none, kat sini ada none, mana? None, alright. It will only stop after completing number of iteration. If we set iteration 1000, stop lah 1000 tu. Right? Kita kira lah. Okay, residual plot shows when the residual value have reached the specific tolerance. Okay, for example, if we set continuity 1 to the minus 5, 1 to the minus 5 sini, so this must achieve lah 1 to the minus 5. Okay, if you set yang hijau, yang kuning ini adalah epsilon. Epsilon must be 0. Kalau di set 10 to the power of minus 3, this means is converge lah. Right? It depends on whatever we have set here. Okay. Dah siap ke kita punya ni? Alright, sudah. Kita kejap kita tengok ini. Okay, atau sambung lecture. Lecture lah. Bismillah. Alright. If there a particular value you are interested, for example, lift coefficients. Okay, for example, lift coefficient, average surface temperature and so on. It's useful to plot how that value is converging. Nanti kita tunjuk dekat kereta tu nanti how we plot lift coefficient like this one. This is number of iteration bawah ni. Okay, as more iteration goes, right, and then the value of CL is become flat. So we consider that it has been converged at around, let's say, 250 iteration. Right? Yang ni kira tadi, okay, in and out must be equals to 0. Alright? Okay. Tightening convergence tolerance. Okay, this one you can change this tolerance to 1 to the minus 6. Okay, if you want. Okay, sometimes running for further iteration is not the answer. Okay, either solution is diverging or blow up, or residual are stuck with large imbalance still remaining. Kadang-kadang bila kita run iteration tak turun pun. Dia jadi naik, terus naik ke atas. Okay, so what you can do is you buat balik lah, ensure the problem is well posed, compute initial solution using first order scheme dulu. Okay, and then we change later using second order. Alter the under relaxation or current numbers, check the mesh quality. Okay, make sure your orthogonality more than 0.01 and skewness less than 0.95. Okay. Okay, you can change under relaxation factor if your solution is not converged. The location is located at kat mana? Solution control, under solution control. Ini tukar ni maksimum 1. Okay, you can change 0.3, 0.2. It's not affected your solution, but it will delay your iteration lah. Okay, delay your iteration. Hopefully the iteration will go down. Okay, okay, tak apa. Solution accuracy. Okay, remember, a converged solution is not necessarily a correct one. Always inspect and evaluate the solution by using data. If you have experimental data, you can compare with the experimental data. Use second order upwind for final results. Ensure solution is grid independence. Okay. If the flow do not seem reasonable, consider check again your boundary condition, check again your mesh quality. Okay, we consider choice of boundaries location in the equal choice of domain. Okay, check balik your punya boundary condition. Right. The use of second order upwind for final result. What is mean? Sometimes kita dah run, okay, kita dah run sampai, katakan kita nak run sebanyak 100 iteration, okay. The first 10 iteration kita run guna first order. Okay. Let's say here we run guna mana momentum biasanya. Momentum we run guna first order. Okay. And then stop kejap, stop. Kemudian tukar kepada second order, sambung balik. You boleh stop, pause lah, pause and change the momentum momentum punya scheme and then we continue. Alright. That is the one way to provide converged solution lah. Right. Okay. Grid independent solution ini sudah explain tadi. Alright. Okay, ini tak ada apa lah. Okay. Summary. Make sure your final result are complete with optimal numerical scheme. All solver provide tools for judging. All solver tools for checking and improve accuracy. Solution procedure for both pressure based and density based is identical. Calculate until you get the convergence. Sama je, you pakai pressure based boleh, density based boleh. Right. Yang penting calculate until you get converged solution. Obtain second order solution. This is highly recommended. Define the mesh and recalculate the verified grid independence results. Right. Solution accuracy will depend on the appropriateness of the physical model that you choose and boundary condition that you specify. Okay. Alright, we go to the car simulation. Mana? Ni, okay, this one. So you have element number 153. Good. 456 ni dah lebih dah ni, 1 million dah. Boleh ke run? Tengok jap. Either nodes or element lah, dan cannot exceed 1510. Okay, this one is already 1 million, the mesh elements. We open the setup. Kalau tak boleh, dia akan appear lah. Tak boleh. So kita kena adjust the mesh number. Lepas tu dah lama kan, mesh dia sampai 1 million. Macam boleh ni. Okay, maknanya yang exit tu adalah node lah, bukannya element. Okay, based on nodes. Tak boleh. Okay, this is student license and can only be used with case containing less than 512 151205. Okay, tak apa. Kita ubah sikit lah. Kita we change the enclosure ni, kita kecilkan sikit. Ini sebagai 30 tadi. Kecilkan sikit. Okay, kecil je. Mana sebenarnya kita? Mana mesh kita? Mesh kita mana? Okay. Ini pangkah dulu. Pangkah dulu, kita buka balik. Nak pangkah pun lambat. Okay, so we open again the mesh. Right. Yes, so abstain data need to be released sebab kita dah tukar dimension tadi. So we need to re-read lah the data. So in the meantime, dekat Lulearn ni, I have uploaded your assignment. Okay. Okay, I have uploaded your assignment. So your assignment just similar to your exercise actually. Okay, just extension a little bit lah. Right. So this is your assignment. This is account for 20% individual assignment. Okay.
So same thing, okay, you can draw, you have a cross pipe made from stainless steel. The fluid flowing inside the pipe is kacau tu. Kejap tiba keluar pula. Okay, the pipe is fluid temperature at inlet 1 is X Kelvin with the velocity V1. At the inlet 2, the temperature is Y Kelvin with the inlet V2. Steady state analysis, by implementing NC CFD analysis, determine the outlet 1 for the outlet 1 and outlet 2, the velocity, temperature and pressure. Okay, the plot graph temperature vs distance along horizontal pipe from inlet 1 to outlet 1, which is from inlet 1 to outlet 1 ni you buat satu line, kemudian plot graph. Okay, so you can submit in ULearn. I state here 18 April, but if you late little bit, it's also okay lah, right? 18 April 5 PM. Sebab apa? Sebab 19 tu you dah ada kelas lain dah. So kalau boleh jangan ambil ni lah, takut delay lambat pula. Okay, before you join other class, you just complete our assignment. Okay, so this is a task given for each student, different dimension. Or this is assignment, so make a proper assignment in terms of report. Must have introduction, methodology, which is engineering data, equations, meshing, bonding condition, material properties, CFD model verification. This is referred to grid test lah. If you want to do grid test, you can do under CFD model verification, solution method, and also convergence, and also result and discussion. Okay, total marks is 100. Okay, so make a simple report using this as assignment. Same with the exercise, but I just changed a little bit geometry. You can draw this in design model, or you can draw using SolidWorks and import into the ANSYS. Okay, this is simple geometry. Right, go back to our. Saya terganggu je kereta ni. Ini belum mesh lagi. Besarkan sikit. Ini 1.3 E2. Saya buat 1 E negatif 2. Okay, generate mesh. Ada soalan tak tentang assignment? Rasanya simple je kan? Lama betul.
So kita cuba habiskan lecture dan demo ni sebelum pukul 12. Okay. Petang ni saya tak buat kelas lah. Jadi boleh study untuk bersiapkan assignment. Nanti saya akan upload juga recording untuk hari ini dan juga hari Selasa. Yang hari Selasa I have uploaded for today. Nanti saya upload. So boleh refer lah. Belum lagi, lambat je. Sekejap banyak lah. Tukar balik. Sekejap. 30. Patutlah. 3 pula. Kalau kosong, default dia adalah 1.3. So you have, let's say, 3E negatif 2. Tadi sebut lagi kecil pula, 1.3 sebab 1. Lagi kecil pula saja. Laju sikit. Kalau lebih juga kita tak nak run kat sini lah. Kena adjust balik lah. Tapi saya ada upload the video. Sama je. Okay, saya dah record dulu. Harap boleh lah ni. Okay, so dah siap. Tengok berapa? 1, 2, 3. Alamak, tak boleh lah. Masih lagi besar. Macam mana nak buat? Tak boleh buat lah ni. Kena adjust lah. Adjust balik ni, besarkan lagi ni. Mungkin 0.1 ke 0.1 ke kan. Okay, kalau tak sempat tak apa. Dekat YouLearn, saya dah upload video. Sama je. Okay, sama je. Dekat YouLearn ni. Okay, under video on run aerodynamic simulation ni. Sini ada. Okay. Dia guna yang sama tapi kenapa? Okay. Machine dia pakai adalah yang saya pakai dulu lupa. Ini saya pakai yang lama lah, version yang lama. Ataupun saya pakai yang version yang full version ni. Okay, mungkin full version kot. Okay. So kalau run ni kena pakai yang full version lah, tak boleh pakai yang student version sebab dia dah exceed limit 512,000 K cells, right? So in the end you run saja macam biasa, kemudian dia akan keluar lah. Okay. Apa ni? Streamline dan semualah kat sini belakang saja. Okay. Sini ada video kita lihat. Alright, boleh cubalah. Sebab kita ni dah lebih, dah lebih daripada limit. Okay, ada soalan tak nak tanya antara tu? Kalau tak ada, saya ingat saya stop sini. Okay, so boleh siapkan assignment ataupun refer kepada video tadi. Nanti saya akan upload our lecture today in Learn, so you can refer back lah our notes, or maybe to complete how to construct the line. Mungkin yang line yang garisan tadi tu mungkin tak buat lagi masa exercise. So boleh refer back lah to the video how to construct the line. Mana? Banyak sangat tabnya. Ni. Okay. Right. So you need to determine the outlet 1 and outlet 2 velocity. You can using probe, you can visualize using counter to show the temperature and the velocity and also the pressure. Okay. Plot graph ni mungkin dalam video yang saya akan bagi recording ni boleh balik. Kalau ingat lagi okey lah. Terus plot je. Alright. Mendapatkan berapakah temperature dekat outlet. So kita expect kalau you guna, pastikan dapat result yang logik lah. If you include input 280 and 350 as an inlet, so outlet must be around this lah, must be around 280 and 350, cannot go beyond 400 Kelvin. Okay, so it is logical lah. Okay, to check your answer. Okay, ada soalan? So,
Doktor.
Ya.
Untuk assignment tu nak submit tu submit report je ke ataupun sekali dengan file NCS tu?
Submit report saja.
Okay.
Report saja. Okay. Format Word lah.
Thank you.
Okay. Sama. Okay, ada soalan lagi? Okay, kalau tak ada boleh kita stop sini. Kalau ada masalah boleh WhatsApp saya, boleh PM saya pun tak apa. Kalau segan nak tanya dalam group boleh PM sajalah. Rasanya Dr. Samsul ada invite group, so siapa yang belum masuk group boleh masuk dalam group lah. Mana ni. Nanti boleh masuk dalam group siapa yang belum ada dalam group. Mana kita punya ni. Okay, saya letak dekat chat box. Okay, siapa yang belum masuk dalam grup WhatsApp boleh masuk. Okay, terima kasih semua. Jumpa lagi di lain hari, di lain ketika. Mungkin nak ambil projek nanti ke last semester boleh hubungi saya lah. Okay, so kalau ada apa-apa kita stop sini. Kita jumpa lain kali. Assalamualaikum dan selamat tengah hari.
Terima kasih doktor.
Assalamualaikum.
Doktor.
Ya, kan.
Selamat.
Thank you, Doktor.